Hello everyone, my name is Rimni Chima and I'll be presenting alongside Kaden Watt. Today we're sharing our work in progress project, the design and development of an immersive VR laboratory for electrical circuits. This project was completed at McEwen University under the supervision of Hussein Samar Kurbani and focuses on using VR to support hands-on learning of introductory circuit concepts. Before going into our project, we'll first explain the challenges in circuit education and why VR could be a solution. So to begin with, electrical circuits can be difficult for students to understand because many of the key concepts like current, voltage, resistance, and overall circuit behavior are abstract phenomenon, meaning that they're not directly visible. Since some learners can't actually see how electricity moves through a circuit, it can be hard for them to accurately create mental models through conventional teaching alone. This often leads to misconceptions on how circuits work across various education levels. There's also a hands-on gap because physical labs are useful, but they can be limited on time, equipment, setup, and safety. VR can help this by allowing students to build, test, and adjust circuits while receiving immediate visual feedback. So what we know and the gap. Previous research shows that computer-based virtual labs can help students understand circuit concepts by letting them experiment, repeat activities, and see a visual representation of ideas that are normally hard to observe. Physical labs are still important because they build real measurement and equipment handling skills, so the goal is not to replace them, but to see how VR can complement them. The gap is that many virtual labs are still desktop-based. They may show simulations, but they don't feel hands-on or immersive. With VR, students can reach, grab, and place and manipulate components in a 3D space, making the experience more active and closer to real experimentation while still providing that real-time visual feedback. For the system design and development, our goal was to create a VR lab where students could actively build and test electrical circuits instead of just looking at equations. The development pipeline started with building 3D assets in Blender and then bringing them into Unity where we can create the lab environment, component interactions, and circuit logic. The project was deployed on the MetaQuest headset using Unity's XR tools to support hand tracking and real-time interactions. The environment was designed as a spaceship-style laboratory to make the experience feel more immersive and engaging for users. Inside the lab, we included interaction tables, storage areas for the circuit components, and a display panel for real-time electrical values. The goal was to create a space where users could easily understand where to pick up components, where to place them, and where to observe the results. The main components in the simulation include batteries, resistors, light bulbs, which students can pick up and place into the circuit. These components were designed to represent basic circuit elements. Users can build both a series and parallel circuits and then observe how changing components can affect the circuit behavior. For example, when a component is placed or removed, the system updates values like voltage, current, and resistance. A key part of this project was the use of natural hand tracking. So instead of using controllers, users interact with the lab using their hands. This allows them to grab, reach, place, and release components in a more natural way. The purpose was to reduce the feeling of using a complicated interface and avoid another layer of learning for students so they can focus primarily on circuit concepts rather than learning new controls. And this also makes the experience feel more hands-on because the users are physically manipulating the circuit pieces in the VR space. For the demo, we start by assembling the series circuit. We start by placing 2 light bulbs, a resistor, and batteries. The batteries provide the voltage for the circuit, so once the battery is placed, you can see the bulbs light up and we get real-time feedback on the screen. Next, we're going to build the parallel circuit. We're going to keep it the same, 2 light bulbs and a resistor, and put the battery in. And as you can see, now you can compare the 2 circuits side by side, check the resistance, check the current, and in the parallel, you can see the light bulbs are brighter because of the branching nature of the circuit. If you remove a component in any part of the series circuit, you can see that it breaks the circuit and the light bulbs turn off because there's no more current running through the circuit. And then in the parallel circuit, each branch is independent, so removing one component doesn't shut off the other light bulbs.
For this study, we recruited 7 undergraduate students from a computer science and virtual reality class at McEwen University. The testing was conducted in 2 rounds. In the first round, participants interacted with the placeholder circuit components in an early version of the VR lab. This phase focused on evaluating hand tracking, object placement, and the overall user interface, while also gathering feedback to improve the system design. After implementing those improvements, we conducted a second round of testing, using a fully functional VR laboratory with working series and parallel circuits. Participants then completed a structured survey. For data collection, we used 3 main instruments: usability questions adapted from the system usability scale, presence and immersion measures from the iGroup presence questionnaire, and comfort measures from the simulator sickness questionnaire. We also included an open feedback section for additional participant comments. Together, the qualitative and quantitative results helped us evaluate usability, engagement, and the overall VR learning experience. Survey responses showed a generally positive assessment of the VR circuits lab. Participants found the circuitry intuitive, and most reported that interacting with the components using a hand tracking felt natural and easy to learn. Many students also said they would recommend the VR lab to other learners, reflecting strong usability and overall satisfaction. Participants identified direct interaction with components, especially the light bulbs and batteries, as the most engaging part of the experience. Visual feedback, such as changes in bulb color, was frequently mentioned as helpful for understanding circuit behavior and seeing immediate system responses. At this stage of development, the bulbs changed color, but did not yet include full illumination effects. Most users also described the hand controls and object interactions as intuitive. However, some participants reported minor usability issues, particularly with the pop-up menu and placing components further away. Responses related to immersion were also positive overall, with participants reporting a strong sense of presence in the virtual environment. Some feedback suggested opportunities to further improve the realism of the scene. Learning perspective, the real-time visual feedback in the simulation appeared to help users better understand circuit behavior. Features such as bulb color changes and live values for voltage, current, and resistance allowed participants to immediately observe the effects of changes in the circuit. Many participants found this feedback engaging and helpful for understanding cause and effect relationships. The ability to directly manipulate components also encouraged experimentation and exploration of concepts such as current flow in the series circuit and independent branch behavior in the parallel circuit. Overall, these findings suggest that the VR laboratory could serve as a useful complementary tool alongside conventional physical circuit labs. However, this was an early stage evaluation with a small and relatively similar participant group, and most users already had prior VR experience. The study also did not directly measure learning outcomes. As a result, the findings mainly demonstrate feasibility and user experience rather than confirmed educational benefits. Future work should involve larger and more diverse student groups, particularly beginners learning circuit concepts, along with more formal assessments of learning outcomes. Future work should also include the addition of other circuitry concepts, such as AC circuits, capacitors, and oscilloscopes, and focus on implementing the feedback from the first rounds of testing.